Starting a new unit today. It is exponential and logarithmic functions. And we'll start off like we do with most units. We'll be looking at the graphs of both of those and the equations, of course, that make those. So an exponential function is of the form f of x equals b to the power x. The domain of this function, no matter what b is all real numbers, and the range is y is greater than or equal, or sorry, just strictly greater than 0. There's a horizontal asymptote on these also at y equals 0. And that's going to be true as long as there are no transformations to the function. And of course, even some transformations would not cause those to change. Okay, so there are two possibilities for b. The b value could be something that's greater than 1, like for example 2 we have over here. When that happens, we have a situation that's known as exponential growth. So it's exponential because it's an exponential function, and it's growth because as we move from left to right on the graph, the y values are increasing. So to draw the picture, I'm actually going to start with the horizontal asymptote, which is at y equals 0. And then I'm going to draw in the function using a basic shape that I know and also a single point. The single point that I'm going to use is at 0, 1, the y-intercept. That's going to be the y-intercept for any of these exponential functions, again, as long as there are no transformations. So when I draw it in over here to the left for the exponential growth function, the curve is going to approach the horizontal asymptote, and then as we cross the y-axis and continue on, it grows very quickly, which is the characteristic that we call exponential growth. All right, so you can see from the graph that all of the values, all of the y values on the curve are above the x-axis, which is matches up with the range that we had there, that the y values are all greater than 0. The reason that 0, 1 is your your y-intercept is because if you put in 0 in place of x in this function, it would say 2 to the power 0, and anything to the power 0, of course, is 1. All right, the other possibility for your b is that it could be something between 0 and 1, like, for example, 1/2. When that happens, we have exponential decay. So that means as we move from left to right on the graph, it's going to be decreasing. So I'm going to again start with the horizontal asymptote, and I'm going to put in the point 0, 1, because 1/2 to the 0 power is still just 1, so it still has that same y-intercept. Now this one is decreasing, so that means as I go to the right, it has to be approaching that horizontal asymptote. And as I go to the left from the y-intercept, well, it's going to be going upward like this. So if I'm looking at this graph from left to right, it is decreasing all the time. So this one is decay, decreasing. Now I want to talk about b for just a minute because we had two possibilities. We had b greater than 1, and we also had b is between 0 and 1. And it doesn't state it directly, but it is kind of implied that b cannot equal 1 for these functions, and b can also not be less than or equal to 0. I don't even know how to write that. Well, let me say this. b is non-negative. That would do it. So the base of this thing can never be a negative value. Okay, just like with all of our other units, we're going to have transformations that we could use with these basic parent functions. So the b follows the same rules that we had up in the top there. If the b is greater than 1, then we're starting off with an exponential growth function. If the b is between 0 and 1, then it's exponential decay for the parent. But then these transformations could cause it to do other things here. Okay, just like with all of our other functions, a is going to be a vertical stretch for compression. That was very messy. And we will fill out a little extra there, just as a reminder. For vertical stretch, that would be if a is greater than 1. And for vertical compression, that would be if a is between 0 and 1. And then if you have a negative in front of the a, then that would be a reflection over the x-axis. Okay, we also have, if you replace the x with x minus h, that h would cause it to shift horizontally. So this is going to be a horizontal shift. And just like all of the other functions that we've worked with, it's kind of backwards from what it seems like it ought to be. So if it says x minus something, that would be to the right. If it says x plus something, that would be to the left. Okay, the last transformation that we'll have up here is the k value. And k is just added on to the end of the function. So just like with all of our other functions, that would be a vertical shift. And that follows the same rules as all of our other vertical shifts. So if it says plus something, it's up. If it says minus something, it's down. Okay, so we're going to go through a few examples here. For each of these, we're going to identify the base of the parent function. So we're going to figure out what b is. I will describe the transformations that occur to create the new function, and then state the equation of the asymptote, sketch the graph, state whether the final function is exponential growth, so whether it's increasing as we move from left to right, or exponential decay, so decreasing as we move from left to right, and then we'll identify both the domain and the range. So for our first function here, the base, the b value, is whatever is being raised to a power. So this can be kind of tricky. On this one, it's a 2. I've got 2 raised to a power of something. So my b is 2. So when I'm starting out with this one, because that b value is greater than 1, that means that the parent function on this one is an exponential growth function. So I'm going to write down what the parent is. And I'm going to use y so that we have less chance of confusion with the function notation there, f of x. So the parent function on this one is y equals 2 to the power x. Okay, now for our transformations, we have an a value of 1/2. I thought I changed that. There we go. So we have an a value of 1/2. So the 1/2 is a vertical compression. By a factor of 1/2. Then in the power, we've got an h value of 3. So that would be translated right 3 units. And then at the very end of this, we have -4. That's a k value. So that would be 4 units down. All right, so let's figure out where the horizontal asymptote is on this one. On the parent function, your horizontal asymptote is at y equals 0. So So if I take that line y equals 0 and I compress it vertically by a factor of 1/2, that's not going to change it at all because that's multiplying the y value by a half. 0 times a half is still 0. If I move it to the right 3, then I'm adding 3 to all of the x values, and there are no x values in this equation, y equals 0, so that doesn't change it either. If I move it down 4, then that means I'm subtracting 4 from all of the y values. Now that one would actually change it. So that one's going to give me a new horizontal asymptote there. So 0 minus 4 would give me -4. Okay, I'm going to use that information in order to sketch my graph now. So I'm going to start with coordinate plane. I'm going to start with the horizontal asymptote then. So I'm going to go ahead and put that in. It's at y equals -4. So that's about right here. I'll just label that -4, and then it has to be there. Now I'm going to put in the y-intercept on this one. It's going to be what the y-intercept was from the parent function, but then transformed however it says on here. So I think I'm going to put it in yellow for the parent function. The coordinates of that point are 0, 1. So then if I compress vertically by a factor of 1/2, that means I multiply the y by 1/2. So that would make it 0, 1/2. I think I'll go ahead and put that up here next to it. So 0, 1/2. That was not nice. There we go. Okay, then if I move it to the right 3, that means I have to add 3 to the x value from that point. So 0 plus 3 would give me 3. So now I'm at 3, 1/2. Then if I move it down 4, I have to subtract 4 from the y value at that point. So 1/2 minus 4 would be -3.5. I'm not normally a big fan of mixed numbers, but for graphing purposes, the mixed numbers really are nicer. So I'm going to go ahead and plot that point there. So to the right 3, and then down 3.5. That would be just a little bit above that horizontal asymptote that I have there. Okay, now the parent function on this one was y equals 2 to the power x, which is a growth function. So using just this one point and the horizontal asymptote, I can actually, I can sketch the whole function. Since it is growth, toward the left, it has to approach that horizontal asymptote. Sorry, since the parent function was growth. And to the right, it would have to go away from the asymptote. So this would be a fairly decent sketch of my graph. Now looking at the graph there, as I move from left to right on this picture, I can see that it's going upward. The y values are increasing, so that means that this would be an exponential growth function. For the domain, with an exponential function, it doesn't matter what you do to it. The domain is still going to be all real numbers. And for the range, well, the range is affected by the horizontal asymptote, really. It's either everything above that horizontal asymptote or everything below it. So looking at my picture, I can see it's all above that horizontal asymptote. So I would say it's all y's that are greater than -4. All right, now you tried the first couple of problems on the Google form, and then we'll come back and do another example.